Welcome back to class. My name is RJ and this is Design for Dynamic Wearables, a course that explores body architecture techniques using Grasshopper. So in today's course I wanted to look at this design for a dynamic wearable skin on a human figure. We'll take a look at how to build this today using Grasshopper and all the different techniques that come with designing a skeletal structure such as this. So to start off, this workflow will be using the plugins Shortest Walk, Pufferfish, and Dendro. So make sure you have those to begin with, and I'll be putting links in the description of this video so you can go download those from foodforrhino.com. So the workflow for today, we're going to look at creating the pattern and then how to offset the pattern from the mesh so that the pipes do not intersect with the mannequin figure that we're using. We'll look at then how to create the pipes using dendro, so a voxelization technique to create those pipes. And then lastly, we'll look at the color gradient, so how to make the final colors on the piece and how you can edit those and make them exactly what you want. So to get started here, we'll use a base human form, and if you have one, feel free to use it. But you can also grab this file from Patreon. Link for that is in the description as well, and that'll have the exact mesh that I'm using, along with the entire definition in Grasshopper that we'll be creating today together. So you can download that there. But to start, we'll be using this mesh. And the first thing we'll have to do is create a pattern on this figure. And the way I like to do that is to use a voronoi workflow. So we'll be creating 3D voronoi cells on this mesh that we can use to map a line system around that we can use to find our pattern. So to start with that, we can use the voronoi 3D, which will create our 3D voronoi cells around the figure. In order to define all of the inputs for the voronoi, we will need points for the voronoi diagram, as well as the bounding box around the shape. That is optional, but we can add one if we need it. So to start with the points, we can populate the geometry, which will put points on the surface of the mesh that we have, and then we can use those points to create cells around each of the points. So we'll start off by plugging in the mesh to the populate geometry. That'll put the points on the surface. You can see as we orbit around, they are just on the surface and not inside or outside of the mesh, just on the surface. We can create a slider to define how many points we want. By default right now it's at 100. So we can maybe start at 100, 2 dots to define the domain, and then the upper bound. I'm just gonna use 1,000 here. So we've got some high numbers to work with if we need them. So we can wire that together, and then if we start to change this, you'll see we'll get more and more points as we move the slider up. So that's working pretty well. We can take these points and plug them into the voronoi component. This will create the cells around our shape. That looks pretty good. One tip for creating 3D voronoi is if you just use the default boundary, so the one that it automatically creates, we might get some issues where the mesh, just like this fingernail here, might go through the voronoi diagram, which when we create a intersection with the mesh here in a second, we'll get a tiny little outline here. And I can actually show with that, and then I'll show you how to fix it. So to create that intersection I was talking about, we can use the mesh intersection, which you can also grab by typing MMX in the search bar. So we can use the mesh intersection, and this will take two meshes and find the intersection defined as a curve between the two meshes. So we'll need to fulfill A and B. We can start by fulfilling B, which will just be the mesh of the human figure that we have. And then if we look at the 3D voronoi component here, we have a list of closed B reps. So we can easily convert these into meshes with the mesh B rep component. And once they're all converted to meshes, now we have the same number just in mesh format. We can plug that into A, and this will calculate the intersection between the human mannequin and the voronoi cells. So once we get the intersection curves, we can see that it'll start to highlight those curve lines there. And we can just go ahead and preview everything else off that we don't need anymore, and we can see what those curves look like. So it's looking pretty good, but we can go back to what I mentioned earlier about those tiny edge case boundaries where we can see the box intersecting. So we'll just get these small outlines here. And if we go back to the voronoi pattern, we can see that that's where the mesh itself is actually extending beyond the voronoi cells. So yeah, it's happening on the other side too. It's pretty easy to fix this. One thing I like to do just zoom out for a second, is we can start by creating just a boundary box on that mesh. So this is going to give us the same shape as we see here currently, but what I like to do is actually scale this up just a tiny bit so we can make the boundary just bigger than the mesh itself, so we don't run into this edge case where the mesh extends beyond the voronoi. So what we can do is plug the bounding box into the geometry input. We will have to use the center point of the box so it doesn't just scale around the origin. If we were to do that, we can grab a panel quick. We'll just scale up just a tiny bit, so 1.2. We'll scale up a little bit. If we do that, we can see the box scales about the origin point, which is not exactly what we want because we might be having the feet extending below, which we want to make sure all sides of the box are accounted for. So in order to do that, we can actually use the center of the bounding box. We can do that with an area component. The area component is going to give us the center point of the box. So if we hide everything, we can see that center point, bounding box right in the center. We can use that point for the scale, and now if we look at the scale, we can see it's scaling around that center point instead of around the origin of our world. So let's bring everything else back. We'll hide this for the time being. And now what we can do is actually use this scaled up bounding box and plug that into the bounding box input of the voronoi diagram. And this will make the diagram extend out to that boundary line. So now we can see the voronoi cells have extended beyond our mesh completely, which is great. So let's turn this off and we can see that the mesh intersection now wraps around and we won't have a risk of any edge cases like that happening in the future. So to keep moving on, next thing we'll do is we'll set up for the shortest walk part of this tutorial. So we'll start by grabbing our shortest walk component, and this will help us make our organic pattern around the body. And we'll use these intersection lines that we just found as the base grid of lines to construct a pattern within. So if we look at our inputs for shortest walk here, the ones that we have to worry about right now are going to be the curve group, and then this last one here, the wanted path. So right now we have the curve group, and we'll have to construct a wanted path so we can start constructing paths in this shape that are a lot more organic than just the standard voronoi cells, which are not very unique at this point. So we can start by exploding these curves, and what this will do is it'll break down all of these polylines into individual lines, and that's going to be the best way to add this into the curve input for the shortest walk. So you'll notice if we look at the intersection of the mesh intersection right here, all these results, they are grafted into branches, tree branches of a list, which we don't need for this workflow. We'll want all of the curves to be on the exact same list because we only want to find paths within one list of all of these lines here. So we can start by right-clicking on the output and just flattening that output. And this will put all of our curves onto a single list. So with all these curves on a single list, we can see that right there, looking perfect. We can plug that into the curve input, and this will break it up into segments and vertices at the exploded segments. We can flatten both of these because, again, we want these all to be the same list. We don't need it to be grafted, not for this workflow, because we want to reference them all at the same time, not at separate times. So once we have the vertices here, what we can do basically is we have all of these vertices, and if we connect lines between any two pairs, we can start to construct our wanted paths. So basically a start and an endpoint and a line to tell the shortest walk algorithm how to set up these wanted paths. And if we have this grid of curves, which is the voronoi diagram on our mannequin, if we give it a start here and an end here, what this is going to do, the shortest walk component, is it's going to look at our entire curve group, which is all the lines that we just exploded here, and it's going to find a path of the shortest distance between the 2 points and give this red line as our result. If we have enough of these lines, we can start to make a very organic pattern that we can use as a dynamic wearable for our figure here. So in order to construct these random 2-point connections, what we can do is take this list of vertices and start to reduce it. because right now we would have thousands and thousands of wanted paths, and that would just be a little messy. So we can reduce it down to something that is more aesthetically pleasing to us, and we can control this later on. But the best way to do this is to randomly reduce it. And we've got this nice component here, which will randomly reduce any list into a smaller list. And then we can use that smaller list to construct our wanted paths. So in order to start here, we've got this input of the list to reduce. We know we want to reduce the vertices to something a little bit more manageable. And we want to do this dynamically. So we don't want to just tell it to remove, 5, 10 items from the list, because if we come back and change this original input of the voronoi, we could have, a lot more voronoi cells or a lot less voronoi cells. And then that input number that we made, reduce 10 points will change. If there's a lot more points, then 10 is going to do a lot less work. But if we only have 20 points, then removing 10 is going to take away half of everything. So we want this to be dynamic so that anytime we update the original input, it only takes away, say, 60% every time or 90% every time. We want that to be reactive to the actual number of vertices that we have here. So how do we do that? We can start by using a list length component. What this is going to do, it's going to take our list of vertices and it's going to tell us with a number how many vertices we have. In my case, we have about 29, just over 29,000 points here. So we can take those 29,000 points and say, only keep 90% of these, or get rid of 90% of these. We could do either. We can do that with a multiplication component. Multiplication will work just as you think. It'll take A, multiply that by B. So if we plug in our number of items here, just above 29,000, we can grab a slider. We'll go 0.001 to 1. Again, 1 is going to return the exact same input number. So 1 times 29,000 is 29,000. Anything lower than 1 though, and will start to give us values smaller than that. So let's put it pretty high here. So we want to remove most of the points, 96%. If we plug that in, we can see that we're now asking it to remove just about 28,000 points. So this will leave us somewhere around 1,000 points right there are left. And we can see that represented in Rhino. The green dots are the points we're keeping. The red is everything we're removing. So let's hide everything we don't need. Just good practice to keep doing this. So now we have a much smaller list of points. And it's important to do it this way rather than, say, just populate 1,000 points, because we'll want the points that we're finding to actually be on the curve group that we began with. So you'll notice if we zoom in, every point that we're finding is on one of these lines. That's going to be very important for the shortest walk algorithm later on. So now that we've randomly reduced the points, we can start making connections between points. We can do this with a partition list, and that'll take any list and break it up into groups of whatever size we tell it. So let's grab that component, partition list. We'll wire our random reduce into the partition list, and then if we want to construct a line contains 2 points, a start and an end. So if each group is containing 2 points, then that can construct a perfect line. We can add a panel with a number of 2 in that panel. And then we can see here the size of the partitions. If we give that a value of 2, it'll now give us tree branches, and every branch has 2 items within it. So 2 points for every single branch. With that, we can construct a line. A line has an A and B input, but how do we go from a single output from the partition list to an A and a B input? The easiest way to do that is with a list item. This list item, if we plug the curve list in, we can zoom in here, and we can, once we zoom in far enough, we can see these plus buttons pop up. Right now, index I is going to be the first value of every single list, so the first point. If we hit this plus button below it, this will be the first value plus 1, so the second value. So now we have the first value and the second value. Since we only have 2 points in every list, we have A and B. So once we put those together, we'll get lines going all throughout our mannequin here. And this is describing the path that we want to try to take between A and B. So for this line right here, we'll say that's the start, at the foot is the end. It's going to try to find a path up the arm, down the body, to finish at the foot right there. So this might not be possible for every single line. Some lines might be starting on an island, in which case you can't connect to an island because it is away from the rest of the group, but that's not a big problem for us, as the shortest walk is just going to ignore those and it's going to give us an orange error probably, but that's not the biggest deal for us. So right before we plug this in, we will want to flatten the line list, just because we don't want to search in different groups at the same time. We want them all to be on the same list so we can have all of these lines at the same time. Similarly, we flattened the segment list earlier, and that's for the exact same reason. We want to use the segments as the original grid to search within, and we want all those lines to be on the same list as well. So we'll want to plug the segments into the curve group and the lines into the wanted paths. But right before we do that, you might be thinking, we have these curves within the Voronoi pattern here. I'll draw it out. So we have part of one of the cells, and then say another cell is next to it. We've got this cell. So one thing you'll notice is they share a line right here. So there's one line for the left one and one line for the right one. Basically saying we have two lines that occupy the exact same space in our grid, which isn't going to be great for the pattern because it's too many lines. We don't need that many lines. We can significantly reduce the number of lines we have if we got rid of all those double intersections. We'll probably even cut our list in half, which will just save on computation time overall and make things easier for the algorithm for the shortest walk. So the easiest way to remove duplicate lines is to use a component from Kangaroo, which everyone should have with Rhino 678. And that's going to be remove duplicate lines. You can see it up here. I like this one a lot, along with the remove duplicate points from Kangaroo. They work really well. We can plug our segments into the list input here. The tolerance by default is 0.01, which is perfect for us. These lines occupy the exact same space. So 0.01 is a large enough number to see that intersection. So if we compare the lists now, we started with 28,000. And coming out, we're at 16,000. So a big difference there. We have a lot less lines. At this point, now that we've cleaned up that list, we can go ahead and make sure it's flat again. So these are all on the same list, which looks good. You can plug that into the curve list, and then we'll take the lines and make sure those are flat as well. Plug those into the wanted paths list. And we'll wait for the shortest walk to do its thing, and it should give us a pattern here in a second. So we can see that it's starting to give us a pattern. We do have that orange error as I expected, and it's saying that no walk is found for these certain points because the end positions are probably on islands, which is fine. It's just ignoring those, and we got everything else. So again, we'll hide everything previous just to clean the visuals up. We do not need that anymore, and we're left with this pattern. So it's pretty close to the Voronoi original at this point. So I might increase this value to 0.99, go even higher, and this should cut down on our pattern. So now we have a little bit more sparse of lines, more open spaces, and you can make this number even higher, maybe 0.999 if you wanted to get even less lines, but up to you with how the pattern is looking on your screen. Okay, so after this, we can clean up these lines a little bit more. Right now, they're pretty jagged as they're following the Voronoi grid exactly, which we want to try to get as far away from the Voronoi cell aesthetic as possible. It's just very overused, and there's a lot of components that we can use in Grasshopper to make it a little bit more unique. One of those being a lot of the options in the curve utilities. So the first thing I'm going to do here is reduce this curve. And what this is going to do, it's going to remove the least significant vertices of that curve, and we can control this with a tolerance. I'm going to go with standard 0.01 to 1 to start us out, and we can plug our shortest walk output, which is going to be the W here, into the polyline to reduce input, and we can start to control this slider here. Let's turn off the shortest walk. We don't need to see that. And you can see how our pattern of lines is changing as we change this curve around. This is just gonna clean up our curves a little bit, make it a little bit lighter for the script later on. Let's just settle somewhere around here. And then we can add a smooth polyline into the mix as well. So we'll plug the polyline into the polyline, turn off the reduce, don't need that. And we can see the line starting to get even smoother. And if we change this reduce slider now, we can see it affecting it a lot more. So the less vertices that a polyline has, the more it can be smoothed out. So if you had a line with 100 polylines in it, there's not much you can do to smooth it because it's so defined. If we had a line that only had 3 points, though, we could really easily smooth out the line because there's not a lot controlling it. So that's what this setup is doing right here. So once you've got the curve pattern to an aesthetic that you're kind of enjoying, we can think about piping this and getting our final look. But before we pipe it, you'll notice that the curves that we're creating are right on the mesh. So let's do a little drawing. If we had the mesh, say this is the inside and this is the outside of a mesh boundary. If we have a curve right on this mesh, then if we pipe it, that pipe is going to extend inside and outside of the mesh, which is not going to be great if we're planning on 3D printing this and actually putting it on someone, because the garment itself is going to be trying to both be inside and outside of that figure at the same time, which, along with being quite uncomfortable, will probably make it impossible to wear. So what we can do is we can move this line away from that mesh. So we want to move it out. And we can do that by taking the normal of the mesh at multiple points. So the normal is going to be the vector that is going off of the mesh. And because this mesh is curved, these normals are also going to be curved. So pointing perpendicular to every point that we look at on the mesh. So once we find all of those normal values, we can move our line, the red line here, away, and we can move each point away at that normal. So even if our shape is pretty curvy, like this, we can still move our line away from it in every good direction, and the line will now be curvy like this. But it'll be in 3D, so even more complex than these 2D. But it'll be in 3D, so even more complex than these 2D shapes here. You might be thinking, can't we just offset the curve and be done with it? But in 3D, we have to think about a lot more complex curvature. So using these normal values will really help solve our questions here. So with that explanation down, what we can do is start by deconstructing these polylines into points. And we can do that with a divide curve. And what this will do is it'll take our curve and divide it into a lot of points. By default here, it's dividing it into 10 points each. But we can grab a panel and bump that up a little bit, maybe 20, up to you. The more points we divide, the more detail we will have in the offset. So we will actually need the original mesh itself. So let's go back to the beginning here. We have that original mesh. What we can do to bring the wire down the line is we can use a generic data component to plug that mesh in, and then we can actually grab this component, zoom out, and move it all the way down here. So let's rename this. This is going to be our input mesh, and we can hit the paint bucket icon to flip this to be a text. And now we can see that this data object has our input mesh on it. So we move the input mesh down, and we have the points from the curves. So what we can do with the mesh is deconstruct it. And this is going to give us a lot more information about the mesh. So if we plug that in, we can visually see that we have all of the mesh vertices showing up. But another thing to note is we also have the mesh normals for every single vertex location. So the normals is going to be what's going to help us to offset these curves. What we have to do now is find which normal is closest to all of these points from our divide curve. And once we match up every point with a normal, we can use the normal to move the point away from the mesh. So in order to find its closest point relative, we can use the component called closest point. There are two here. One of them is plural. We do not want that one. We want the singular closest point. We only want to find the one closest point. So to wire this up, we want to search from the points on the curve to the points on the mesh. Because if we're searching to the points on the mesh, let's come over to this closest point component here. And if we look at the output, so these are all the points that will be output, it's going to find the point in C, the C input here, closest to P, so the P input here. So it's going to output information from C. And we want information from C because we want the normals to use later on. So we'll put the vertices into C. And again, we're using vertices because we can only find closest values between points. We cannot find a closest neighbor between a point and a normal. But if we find the closest value between 2 points, we can then infer that the normal will match up with the vertices, and we can use that normal to move the points. That might be a little confusing, but we'll build it out and see how it works. So we can plug the divide curve into the P input here. What this will do is it'll find the closest neighbor, and we can visualize that just with a line. Again, this is only for visualization, not for the script itself, but we can use this to see what's happening. So to set it up, we can plug the P points into A, and then the closest point result into B. And what that is going to do is it's going to show us the line connection between the point and its closest neighbor. So let's, for visual sake, turn off everything we don't need to see anymore. And if we look at the points we were starting with, so A, we can see that the line started A, and then if we look at the closest point neighbor, we can see that defines B. So we have A, and we have B. And B is the points from the original mesh that align with the normals. So we don't need this line component, that's just for visuals, but we can use the index of the closest point to find the normals from this list. So if we found that vertex number 1 was one of the closest components, we also know that normal number 1 is the normal that corresponds with that vertice. So we can use a list item to do that comparison. List item, it needs a list input and an index input. So we know we have the index of the closest point here. So we can plug those i's together, and then we know we want to find the normals based on those indices. So we can plug the normals into the list input here. So this is finding our normal values, and with these normal values we can use those to move the points. So we can use a move component. This will take a geometry and a movement vector. So we have the geometry, which is going to be all of the points from the divide curve. You can see by default they're moving up by 10 units on the z-axis, which if we hover over the translation vector, makes sense. X is 0, Y is 0, and Z is 10. But we don't want that. We actually have the movement vectors that we found from the normals, so we can wire that into the translation vector. So you can see they're all moving away from the mesh now, relative to their position on the original mesh. So each point is moving in its own unique direction. But we have no control over how far these points are moving away from the mesh, which will be important because right now we could only have a pipe of a single radius, which looks like the radius would be pretty big. And if we want a smaller radius, we should probably also move the points a smaller distance away from the mesh. It's pretty easy to do though, and we can use the amplitude component. This will take a vector, so we have the vectors, and it'll take an amplitude or a length value and assign each vector a specific length. So right now I believe it's at 1. If we wanted to do a lot less, like 0.5, that'll move every point half as much. So let's get a slider. 0.1 to 1 should do it. Let's start at 1. We can plug that into amplitude. Once both of those values are defined, we can take our Once those values are defined, we can take our vector and replace it with the translation vector from before. You can see right now there's no difference because we still have a movement of 1, but now we can move this slider, and as we move it down closer to 0, those points will be moving less far away. So now we have those points just a little bit off the mesh. So again, let's hide everything we don't need. So we only see these final points. Now it's a little bit clearer as the points move in and away from the mesh. You could, just as a tip, make this number negative and the points will go inside the mesh. Don't know why you would need that, but you could do it. So finally, let's take these points and actually reconstruct lines. We had lines, we transitioned them into points, we moved those points from the mesh, and now we need to go back to lines to have our final geometry. We can't do much with points. So in order to turn it back into curves, we can use any of the curve tools, but the one I like for this method is going to be the interpolate. So this interpolated line makes a very smooth curve between every single point. You could use polyline, but that'll make straight line connections between every point, so up to you. We do see that we have this red bubble coming up saying we have insufficient points for a curve. That makes sense. There could be curves with 1 point, which you can't make a curve out of that. What we can do to clean this up, it's not an issue right now, we're still getting curves, but if you wanted to have the cleanest script, we could put a clean tree between the two, and if we set this remove empty to true, we could either do that with a true toggle, or you could right click on E, come down to set Boolean, and just change this to true. Changing it to true will remove all empty branches, and now that there are no empty branches, every branch has enough points for a curve and the error goes away. Pretty nice. Let's remove everything we don't need and continue on. So right now we have this asymmetrical pattern of lines on our figure. You might like that, you might not. If we want something more symmetrical, we can pull from pufferfish and use a component called mirror cut curve. So mirror cut curve, we can take that, and we care mostly about these first two inputs here. So the curves to mirror cut, and then the mirror plane that'll define how the cutting happens. So first things first, the curve to mirror cut. We have the curves here. Let's look at this output here. They're all in separate branches. That isn't necessary for our workflow because, again, we're making one garment, and if we have all the curves on the same list, that'll help us in our quest to make one thing. So we can take all those curves, put them into mirror cut curve input, and then we need to fulfill the mirror plane. So which plane should we choose? If we look down at the compass in the bottom left of Rhino here, which is right under my face, so if we turn those off for the second, we can see the compass down here in the bottom left of Rhino. You should have it as well. And as we move around, you can see the compass is changing as we move the camera. So if we look head on with our mannequin, we can see that the plane that is also head on is going to be YZ. So that YZ plane is going to bisect the body straight down the middle. We can also look at the grid itself and see that the green line is bisecting the body, and green is for Y, red is for X. So we know that we need the YZ plane, so we can double click, type in YZ, we'll get a YZ plane. We can plug that into the mirror plane input, and look at that, we have a curve system that is symmetric on that plane. So one thing we can also do is look at the flip direction. If we want to change this, let's just set up a toggle to make this easy. Boolean toggle, put that into the F input, and now we can flip between true and false and see different outputs based on which side of the mirror plane we are pulling from. So if we pull from the left side, we get this. If we pull from the right side, we get this. So two different results for the same operation. So to finish this out here, let's just pipe all of these curves so we give them some thickness. Again, we're making one thing, so if we see it in branches, let's just flatten the list again. So now we have curves in a list. I do see some null values here, so let's go ahead and clean this list again and check the list. The null values have gone away. Good to see. And we can create the pipe. And the best way to do that, at least for 3D printing, is we can just use dendro, which is a voxelization tool, which will make perfect meshes very, very easily. So we can begin our dendro process by using the curved volume component. This will take curves, add a radius, and convert that into a voxelized volume. So to start, we will always need a settings component. This is very important for any workflow in Dendro. We need settings. Basically, if we think about voxels, we have a cross-section of a pipe here. Voxels are like 3D pixels. So I've got a 2D drawing here, so I'll just do boxes. But basically, if you have a very large settings value, you'll have very large voxel shapes, which won't be too refined for anything curvy. But it'll take no computational time at all to make really big voxels. If we want more detail, we can make smaller voxels, which will add a lot more voxels and fill up the shape much more refined, so we can see those curves a lot better. So basically what the settings are doing is defining how big the voxels are, really big or really small. And we can use that to define the detail of the final mesh. So I like to start by using a slider from 0.01 to 1. Let's start at the higher range because, as I just said, anything really small will take a lot of computational power to do, and we can hone in on that. So let's start really big at 1, and we can get smaller if we need to. So we've got the settings, we'll plug that in. Let's do another slider, 0.1 to maybe 5 this time. This will be the radius of those pipes. Just a tip for you, the radius of the curved volume needs to be at least 33.3% larger than the settings value. So that's why I put this up to 5, so we have more room to play with. So radius, we'll plug that in. And we have the curves as well, so we'll plug the curves into the curve input. So we've got a result in Rhino. It's pretty thick right now, as I expected. We'll have to hone this in to something more refined that's actually going around the curves that we set. Again, let's turn everything off for clarity. So just these curves. Let's start by bringing the voxel size down. The detail goes up, and the time to compute is also going up slightly. You can see by the profile. You can see by the profiler time here. So the detail is up, but the pipe is still pretty thick. So let's bring this value down as well. As we bring this down, you can see the pipe becoming more refined around the mannequin figure. So it's kind of hard to see when everything is the same color. So let's take a custom preview in here with a color swatch. Set this to light gray. And we'll just plug that in. So now we've got a more opaque view, less transparent view of what the pipes are doing. So let's take this radius down even more, 0.5. We can play with the detail here. You can see it doesn't even work at 0.35, but down here it's pretty squishy, but as we refine it more, it gets sharper detail. So that looks pretty good right now. And we've got a couple more settings in Dendro that we can play with, one of them being the smooth volume. And we can start by plugging the volume from the curve to volume into the volume input. Let's update our preview to show this component now. Turn everything else off. And we have control over the smoothing iterations down here. So this will take an integer. So let's just go 1 to 20. We can plug that into the level of smoothing value here, the iterations. And as we put the iterations up, you can see our pattern is getting smoother and smoother. So we started with something pretty refined. We can see like the dimples in the mesh here. If we bring this up, that'll smooth that out a lot. Any of our thin wires will get even thinner, and any of the thick sections will get pretty flat as we start to smooth this out. If we go too thin, we'll start to break the connections, and it's super blobby again. So let's go somewhere in the middle. Looks pretty good there. But up to you, however you want to control this. We have some other settings for smooth the volume as well, which you can definitely play with to see different smoothing options. But now that we have the mesh looking in a pretty good state, we will convert it back to an actual mesh, and we can do that with a volume 2 mesh component. Again, anything with the volume settings needs a volume setting component, so we'll grab that as well, create settings, plug that in. We don't need to define any values here. It'll work without that. And let's just plug the volume into volume. And now we have an actual mesh with faces and vertices coming out. So we'll update that custom preview again, and now we're seeing the real final mesh, no longer a volume. Now that it is a mesh, we can do a lot of other operations in Grasshopper on it. The volume is only accessible in a dendro workflow, so once we exit the dendro workflow, we have mesh again, and we can use that much more broadly than we can a volume. So for the final part here of this workflow, let's add color to the garment, and we can do that with a gradient component. The gradient will define our color, and we can use an attractor point. So we'll grab a point here to control where the color starts, and then all the points far away will be the fall off to the end. So with this point, we can right click, set one point. In Rhino, we can set a point on the grid. Let's come back to the point. We can use the handles here to move this point about. One thing you might note when setting this point is that we want to see type coordinate up here. If you don't see this, we can click on it. We've got options here, coordinate, point, or curve. We'll want to use coordinate, and then we'll set our point. Using coordinate means we can access the point from Grasshopper itself. It doesn't actually exist in Rhino. And this is nice because anytime we click on it, we get these handles, and we can move the point wherever we want in the scene. So I'm just going to put mine right in the middle of the mannequin here. Looks pretty good. And we can use this as our attractor point. So let's right click and just name that attractor point. We can click on the icon to change that to a title. And now we can see it's listed as attractor point. So in order to add color to this based on the attractor point, we can first start by deconstructing the mesh of our pipe. So the gray part here. So we'll plug that into the deconstruct mesh. This will give us all of the vertices of the mesh. And just like how the normals are related to the vertices, the color values are also related to the vertices. So we can find the distance between the attractor point and the vertices. We'll do that just with a distance. We can plug the vertices into A and the attractor point into B. This will take a distance for every single point on our mesh. And we can use those as values for the gradient. So any of the points that are really close to the attractor will be this pink here, and any points that are far away will be this darker red. So in order to define that, we can use a remap, and the remap will take our list. So right now we've got numbers like 39, 6, so it's kind of all over the place. The best way to clean this up will be to remap this domain to be within 0 and 1. That's what the gradient likes by default. So lower limit 0, upper limit 1. So we can remap to be within that domain. We can use the bounds component to grab our initial bounds. So if we plug our distance values into the input here, we can see that our bounds currently are between 2.7 and 39.5. So that is our starting domain. So we've got 3 inputs for the remap here. First one being the values to remap, which will be our distance values. We want to change those. Next input is the source domain. So we know we're starting at 2.7 to 39.5. And then our target domain, which by default is 0 to 1. So we don't need to make a change there. We can just go ahead and plug the remap numbers into the lowercase t parameter input here. And now our values are perfectly aligned to the gradient. So each vertice in the mesh now has a value between 0 and 1 based on how far away it is from the attractor point. So with that all set up, we can use the mesh colors. So with that all set up, we can use the mesh colors component, and this will take a mesh. So we have the original mesh before we deconstructed. So we'll take that into mesh, and now we have colors from the gradient, so we'll plug that into colors. And let's just hide everything we don't need to see anymore. And now we can see we have a gradient on that mesh garment there. and we can preview on this attractor point again. And if we move this point around, we can see we can move the gradient around with it. So anywhere the point is going to be light pink. Anywhere where the point is not is going to be a darker red. So we can also have a lot of control over this gradient value. There are presets that come with it. So if you right click, we can look at the presets, see a black and white, this brown to beige, heat map, red to green, a rainbow, so all the colors, or a black and white zebra stripe, so that as well. And we can also edit these colors. So if you right click on any of the dots, we can change the color that they are. And we can also move these points around to control the fall off between the two colors. So if they're pretty close, we'll have a sharp fall off, and if they're far away, we'll have a very nice gradient between the two. So let's just go as drastic as we can. So there's a pretty even gradient spread across the piece. So with that, we can bake this mesh into Rhino. Let's preview this off. And if we put it into Arctic mode, we can see the ambient occlusion on the mesh. So there's some shadows on it, which looks really nice. We could also bake in the original character as well. So we'll bake that. Now we get those shadows playing between the garment that we created and the mesh underneath. So that looks pretty nice for screenshots and process photos. And at this point we can select the mesh and export it for printing if you wanted to actually make jewelry, body architecture, garment, wearable piece out of this. So hopefully that was insightful. If you did follow along with this workflow, please feel free to take screenshots and tag me on Instagram at robot.objects. The link is also in the description. And as always, these workflow files that we created today, all of the grasshopper will be on Patreon, so you can get those there. And any other files like the original base mesh and any plugin links, those will be in Patreon, and also links in the description for any plugins that we used today. So go check those out. Hopefully this was helpful, and I'll see you next class. Bye.